Now we're going to look at what's called the dual problem. It's minimization problems, but using something that we already know how to do, and that's maximization problems. That's where dual comes in. But a standard minimum linear programming problem has to take on the following form. The objective function has to be minimized. All the y subvalues, now we use y's and not x's to make it different from the get-go, but all the y subvalues have got to be greater than or equal to 0. They have to be, positive or 0, similar to what we've had before. But now the linear constraints, in a maximization problem, they are all less than or equal to, but these are going to be all greater than or equal to. Still, we have a positive constant, or a non-negative constant over here. Now, the fundamental theorem of duality. If either the primal problem, the prime problem, or the dual problem has an optimal solution, then they both have an optimal solution, and their objective functions have the same values at these optimal solutions. It's really cool. Now, if both primal and dual problems have a feasible solution, then they both have an optimal solution, and their objective functions have the same value at these optimal points. The solution of one of these problems by the simplex method yields the solution of the other problem as the final entries in the columns associated with the slack variables. So we've got to go through these, through the steps, through the procedure, so you can see how it works. First thing we've got to know about is what's called a transpose. The transpose of a matrix is obtained by interchanging rows and columns of that particular matrix. So in the next little example, it says find the transpose of the following matrix. The transpose is indicated by T. It looks like an exponent. But the transpose is asking you to interchange the rows and the columns. So this row, first row, is going to become the first column. Second row is going to become the second column, and so on. So it started out as 3 by 4. Notice it's 4 by 3 if we're interchanging rows and columns. So we've got to know how to do a transpose, so that's not too bad. Now the next problem we have done before, it's the graphical solution because I wanted you to see that it does work. And I did use y's because we are trying to minimize. I did it, I did my feasible region, found this, and I found all my corners and my objective function. So my minimum value occurs at this corner point, and the minimum value is 9 1/11. So we got to keep that in mind. We'll be back. So I'm going to take this problem, go to the next page, and we're going to start looking at the procedure. So we're going to construct the dual in order to use the simplex method. First step, put original problem into matrix form. No slack variables. You also include the coefficients of the objective function, not their negatives. This is sort of different. Now we're using this so that we can use the transpose. So really, I just take the coefficients that I see and plop them in the matrix as is. So this is y1, y2. Notice the 12 and 16. Notice that I take these as is and plop them in. Next thing I do is find the transpose. Transpose that right there and I get this. Notice my row here became my column, second row, second column, third row, third column. Okay? So really it's not too bad so far. Now, third thing, from this matrix, this is where we write the dual. These are now going to be x subvalues. So 3x sub 1 plus x sub 2 less than or equal to 2. X sub 1 plus 4x sub 2 less than or equal to 1. This is my z. Notice you take it straight off the matrix. But now, this is what we've done. So you see, step 1, step 2 is not that bad because it gets us back to something that we know how to do. So change these, add your slack variables, get them in the correct form to put it into a matrix. And I put them into my matrix. Excuse me. So I'm going to have an arrow coming up right here. That's my most negative. I'm going to have an arrow. Let me see. This is 2 divided by 1. This is 1 divided by 4. So my arrow should come in right here. And that means this should be my pivot. So see if you can get this. You might try it a little bit later. Okay. I still have a negative. So start here. So if I do my division, I've got 7/4 divided by 11/4. That gives me 7/11. 1/4 divided by 1/4 is 1. So my pivot should be this column, or excuse me, that row. So let me get that. I need to make that a bit bigger. So make the new pivot a 1, everything else in the column 0. Okay. Now, if this were a maximization problem, my x sub 1 would equal 7/11, x sub 2 would equal 1/11, s sub 1 and s sub 2 would be 0. My z value, my maximum value, would be 100/11. But guys, remember this was a minimization problem, and this is where you've got to remember, let me get right back up here, what we did right here. We transposed. My original problem was this way, but when we transposed, it made it going down this way. To read a minimization problem, this is my minimum value, but where the s sub 1 is, this is my y sub 1 value. My s sub 2, this is my y sub 2 value. So if you'll look back on the prior sheet, on page 9, look and see what my corner was. So you've got to be careful. Now, one thing I'll do to you on the test is I'll give you 2 problems, and I'll say this is the final tableau for a maximization problem, and you'll have to read me the solution. Another problem I'll do is this is the final tableau for a minimization problem. So in a minimization, yeah, max and min values is always the slower right-hand corner, but depending on what problem it is, you read it differently. So whatever your slack variables are, this becomes my y1, my y2. Okay, and you read down. So my y1 is 32/11 here, while my y2 is 36/11. Okay, so now in the next video we're going to do a minimization problem from the very beginning. So look back over this, make sure you know what's going on, and we'll try an example. All right, thank you.